Let's recall that we already have a practiced algorithm for adding or subtracting rational expressions together to get their sum or difference. Partial fraction decomposition gives us a way of reversing that process. When decomposing a rational expression into a sum or difference, we start with one that is proper, which means that the degree of the numerator is less than the degree of the denominator. There are two cases where the denominator of that rational expression would have linear factors. The denominator could factor into linear factors that are not repeated, or the denominator could have at least one repeated linear factor. In this video, we'll demonstrate case 1. So again, the overall objective is to split this rational expression into a sum or a difference. To start, we'll notice that our rational expression is proper because the degree of the top is less than the degree of the bottom. So then we want to factor the denominator to determine what case we have. And this denominator factors into x minus 3 times x minus 2. And what we can see is that the denominator contains linear factors, neither of which are repeated. A repeated linear factor would have a higher power on it. So these linear factors both have degree 1, and so they are considered non-repeated linear factors. To begin, we're going to write down the factored version of our rational expression. And here we have our steps outlined, so we'll try to follow along with these. We've already factored the denominator. The case 1 scenario says that we want to have a unique fraction for every factor of the denominator. And in the numerator of those fractions, we're going to have constant values, and these constants will be our unknown quantities. We're trying to figure out what these fractions are going to be. So to come back to our example, we're going to create a unique fraction, one for each of the factors in the denominator. And we have some unknown constant in the numerator, which is what we're trying to figure out. And then to that, we're going to add another fraction for the second factor in the denominator, and this fraction is also going to have some unknown quantity in the numerator. Again, we're trying to figure out who were the fractions that were added together to come up with the proper rational expression that we started with. So the idea is that we need to solve for a and b. So in order to solve for a and b, we start by simplifying, and we'll multiply both sides by the LCD. So let's come back up here to our equation. We are going to multiply both sides of this equation by the LCD of all the fractions. And we'll multiply it by the LCD over 1 because we're going to be distributing that into all of the terms on both sides. The least common denominator in this case is going to be x minus 3 times x minus 2. And again, this LCD is going to be written over 1. So we start by multiplying the LCD on the far left. And when we do that, the x minus 3 and x minus 2's are going to cancel with both of those. And on the left, we're going to end up with just that x. Now let's multiply the LCD by the first term on the right. This time we have x minus 3 that cancels with the x minus 3. So what we have that remains is the numerator a times x minus 2 that did not cancel out. Now let's multiply the LCD times the last term. This time the x minus 2's are going to cancel, and we'll get b times x minus 3 that remains. And so let's write that down here. So multiplying by the LCD on both sides enabled us to clear the fractions and simplify quite a bit. The next step is that we want to rearrange our terms so that we get all of our x squared terms together, our x terms together, and our constants together. So in order to do that, let's distribute our a into the parentheses and our b into the parentheses. So we'll get a times x minus 2 times a plus b times x minus 3 times b. We were also told to get our like terms together, so let's put our ax term and our bx terms together. And then we'll write negative 2a minus 3b after that. Now we're going to factor out the x's from our x terms because we need to be able to see what the coefficient on x is on the right-hand side. So we'll factor out an x from these two terms, and we'll end up with a plus b, which we are going to refer to as the coefficient on x on the right. This minus 2a minus 3b term here is considered to be a constant because there are no x variables involved. Remember, a and b were constant values that were in the numerator of these fractions. So when I have minus 2a minus 3b, this is still some constant quantity. So essentially we have a variable term here because a plus b are the coefficients on the variable x, and then this is considered to be a constant term. Now in our steps it said that we wanted to compare coefficients. As an aside, let's consider the situation when we have 4x plus 2 is equal to ax plus b. When we have an x term on the left-hand side of the equation and an x term on the right-hand side of the equation, and these two equations are equal to each other, then in this scenario we can see that the a value has to be equal to 4. And the constant 2 would be equal to the b term that does not have an x on it, and so then we would say that b is equal to 2. So this is what we're going to do. We're going to look for the x terms and we're going to set their coefficients equal to each other. And the way that we talked about that in the steps was that we were comparing coefficients. So back up here to our problem, we see that on the left-hand side, the coefficient on x is positive 1. On the right-hand side, the coefficient on x is a plus b. So that tells us that a plus b has got to be equal to positive 1 if these two sides of the equation are going to be equal to each other. Similarly, the constant on the left-hand side has to be equal to the constant term on the right-hand side. Since there is no constant term on the left-hand side, we can assume that the constant was equal to 0. And so that means that negative 2a minus 3b has got to be equal to 0. So when we compared coefficients, what we were able to achieve is a system of equations that contains only the two variables that we're trying to solve for. So we can just solve this system. And one way that we go about doing that is by converting it to a matrix. So my top row would be 1, 1, 1, and the bottom row would be negative 2, negative 3, and 0. And this would be an augmented matrix. And the columns would represent the coefficients on A, the coefficients on B, and the constants to the right of the equal sign. So now we'll put this matrix into our calculator and come up with its reduced row echelon form. So we'll say second matrix. Matrix is above the reciprocal button in blue. And we'll go over to the right so that we can edit matrix A. And this time our matrix is a 2 by 3. We have 2 rows and 3 columns. And the first row is just 1, 1, 1. And the second row is negative 2, negative 3, and 0. Second quit takes us back to the home screen. And then we'll use second matrix to pull the matrix A onto the home screen and display it. This clearly displays matrix A, and I can check my input. It also saves this matrix into the answer variable. So now I'll say second matrix and then go to the right one to get to the math menu, and we want to go down the list until we get to reduced row echelon form, which is RREF. Hit enter, and then we'll say second answer in order to operate on the matrix that is now in the answer field. We hit enter. And so what we now have is our matrix in reduced row echelon form, and that's 1, 0, 3, 0, 1, negative 2. And when we return this matrix to the system, remember that our first column is the coefficient on A, the second column is the coefficients on B. This first row turns into A is equal to 3, and the second row turns into B is equal to negative 2. So A is 3 and B is negative 2. Let's take those quantities back up to the beginning of our problem because the values of A and B are what we were trying to find. Those values enable me to split this rational expression up into the sum of two fractions where A was the number above the x minus 3 factor and A turned out to be positive 3, and B was the quantity that was over the x minus 2 factor and we found B to be negative 2. So we've successfully taken a proper rational function and decomposed it into a sum, but we could consider this to be a difference if we said 3 over x minus 3 minus 2 over x minus 2. But either way, this rational expression has been decomposed.